If you look at these two graphs, we see different infinite behavior. Here, if you take x large negative or x large positive, we see the images, the fx, so the y's, are approaching 0. So here we can say that we can describe a certain behavior here. We have, so limit, we write fx as, or let's, yes, so my fx here, I know it's 1 over x2, so let's write it directly. Okay, so just write it. So 1 over x2 as x approaches minus infinity is 0. Here also behavior here, limit of fx of 1 over x2, okay, 1 over x2 is also 0 as x approaches plus infinity. Intuitively, this is we are seeing as x takes large values, and when you divide 1 over large number, we are expecting a number that is very small, that is approaching 0. Okay, so we describe this behavior like that. Another behavior now, if you look that when your x here is close to 0, the fx, you see if an x is here, you look at the, for example, you look at the images, okay, the values taken by f, okay, you look at values taken by f, okay, you see here they become larger, and intuitively, indeed, this is what we see. We can express this behavior here as, okay, or let's, where can I write it? Let's write it here as x up, but it's more here. Okay, limit here I can write limit 1 over x2 as x approaches 0 from the right. Okay, I have, you see, two behaviors different. X from 0 plus, I have plus because my function is not defined one at 0, so I have to precise this. Okay, and from the other side I have this behavior, limit of 1 over x2 as x approaches 0 minus is equal plus infinity also. It takes positive values. Okay, so yeah, so like that, yeah, we have then these two behaviors. Okay, two kind of behavior. You limit at infinity when x is large, you have finite number quantity, and the limit is infinite when you are approaching a fixed number. Okay, sorry. Okay, this okay, so another behavior is this one, and just correct this part, 1 over x2 equals 0. So let's look now what is happening on the other graph here, x3. Well, here, when x is large, we intuitively, taking the power to 3 of large number, we get a bigger number. So it takes large values. Okay, so here we can describe that limit of x3 is plus infinity as x approaches plus infinity, and here limit, okay, and the other behavior is limit x3 equal minus infinity large negative as x takes large negative values. Okay, again here remember that plus infinity or minus infinity are only symbols. Okay, so be careful, this is important, they are not number. Plus or minus infinity are symbols. Okay, symbols that describe behavior. Okay, so this uh, so these are the three kind of limits at infinity. Now so intuitively we were expecting this behavior. Now let's give the precise definition for that. Okay, so try to to understand it. Here it is. So we will say that limit of fx as x approaches x0 equal plus infinity. For example, I'm approaching 0 and I want a behavior that is plus infinity. When can I say that? I can say that if and only if each time I give myself, each time I am considering a level, a large value here, imagine here, a large value m, okay, y equal m. Each time I'm giving, because I want to go to be sure I am always going farther. So for any limit I'm giving myself positive like that. I can find I want to be close to x0, which is 0 in this case. I can find a neighborhood, so a small interval, okay, such that for the x close to this x0 less than delta, all the x's we have, okay, we have what we want the fx to be large, greater than m. Each time I am giving, each time I give myself an m large, I am able to find small interval here close to x0, so that all the fx take that for the x's in the small interval, the fx remain greater than m. So when we have this behavior, then we can say that we can write this describe f going to plus infinity as x approaches x0. Okay. Similarly, we can say limit so we can x0 fx equal minus infinity. If similarly, look, I will say if I'm positive, there exists a delta positive. This time I want my my fx going to minus infinity, so negative values. So I need to have fx remain less than minus m. Okay, since I choose m positive. Okay, so if I can check this definition, then it's okay. I have this. And we can check it here for our function 1x2, 1 over x2. Okay, but I prefer maybe first, or yes, continue the limits, the different limits, then I will apply the limits for just my 1 over x2. Okay, just one case so that you see how it works. So now let's write first as x approaches now plus infinity. We want it to be a limit, a fixed number, like here the y approaches 0. Okay, so we will say that if and only if what, this time the fx, the y's, I want them to be close to L, so I need to control it by the epsilon. Okay, for any epsilon positive, then I can find an x large. Okay, there is and let's call it a, okay, positive, such that for any x greater than this e, then the fx minus L remain less than epsilon. If I can check such a definition, then it's good. And similarly, we can guess, generalize for minus infinity, if and only if epsilon positive for any a positive, for any x less than minus a, then you have fx close to L. Okay, so this is the precise definition. So let's just quickly give an idea of the proof for y is check the limit that 1 over x2, for example, as x approaches 0, equal plus infinity, for example. Okay, so for this one, we need to choose an m, let m positive, so there is no restriction. We are looking for a delta so that we have an fx greater than m. I want fx, which is 1 over x2, greater than m. This is an inequality, so it will happen. M is positive, so I can divide and move my term, so I will get this. This is equivalent to absolute, if you take the square root both sides, less than 1 over m 1 over 2. Okay, so finally I found it. I am approaching 0, so choose. It's enough to choose delta equal 1 over square root of m. Then what happens for the x minus 0, which is absolute value, less than delta, I have, because I have an equivalence here, I have my fx, okay, 1 over x2 greater than m. So you see how the definition is checked, okay, is verified. Okay, so we have exactly this behavior. Similarly, for 1 over x, we prove it. So there's basic limits. You can use them now. You know them. Okay. Now, let's give the precise definition for the third behavior, infinity to infinity. Okay, infinite. Let's give just one, and you can guess the other one. Okay. So for x3, the other behavior is the following. There it is. So we said limit this time. We want limit of fx, for example, plus infinity equal plus infinity. Okay, so this again, I will give myself any m positive. I need to find an a positive such that for any x greater than this a, then my fx remain greater than m. Okay, and etc. etc. You can all express the different situations. Okay. So in particular, an example, so now you know that limit of any xn, we can show it easily, is plus infinity as x plus infinity. Okay. At minus infinity, it's little different, so it behaves depending on the power. Okay, as x approaches minus infinity, so it will be plus infinity if n is odd, and if it will be minus the opposite. I think it's the opposite. So it will be minus infinity if n is odd, and plus infinity if n is even. And you can see it, okay? And these are basic limits that you can use to justify your limits later, okay? Okay, great. Now, another last definition, important definition, is this one. Look at this. Let's come back here at this curve. So here also we have, or just come back to the previous curves. So these lines are important because they describe that my curve is very close to this. Because when our purpose studying a function, we want to have a global behavior. We want to control what is happening very far at infinity. So we need to know how it is. Now, when I describe that my curve is very close to such a line, so this line is important. And this one also, when I say that it takes y very large, but remaining close to the line x equals 0, this line becomes important, and then these kind of lines are called asymptotes. Okay, so the asymptotes, so when you have, so maybe let's just add the terminology here, just close. Okay, So for this situation, let's choose another color, the blue maybe. Okay, let's choose a blue color. So here I will say the line x equal x0 is a vertical asymptote. Okay. Okay. Here y equal L is an horizontal asymptote. Okay. Okay, so this is what you should know. Okay, globally about the limits involving infinity. And the idea when you work on your function, on your formula, usually we bring ourselves to this limit 1 over x and 1 over x2 or xn, where we know what are the behavior. Okay, so if you look now at this, just as an example of application, so the asymptotes here, I can see that my function is not defined at 1 and minus 1, and at these values I have infinite behaviors. Okay, so I have infinite behaviors. So visually, without going through the calculations, calculating limits, I can say that x equal plus or minus 1, okay, are horizontal asymptotes. Okay, asymptotes. And is then are vertical, sorry, are vertical asymptotes. Which one is the horizontal? So the horizontal is this one. Those are vertical asymptotes. So let's correct it. Vertical asymptote, okay, or vertical asymptotes. Y equals 0 is an horizontal asymptote. Okay. So this is mainly what I wanted to show you today. So you need to know so intuitively what is the meaning of behavior, infinite behavior, or limit at infinity, how we are controlling the definition. So we should check the definition to say then that the limit, to write that the limit is like that or not. And the asymptote, the importance of asymptotes, vertical or horizontal asymptotes.